Okay, so in this session, we will discuss about torque, the concept of torque in the case of a DC motor. So when we talk about generators, we usually talk about electrical quantities like induced EMF, current, etc. Whereas in the case of DC motor, we usually talk about the mechanical quantities or mechanical terms, speed and torque. Already we have discussed about the speed, back EMF and the voltage equation and power equation, etc. And in this session, we will discuss further, that is about the torque of a DC motor. What is the torque? Which are the types of torque in the case of a DC motor? And we will derive the expression for the various torque. So what is torque basically? It is actually force into distance. That is the torque, right? So torque is measured. In simple terms, you can say that torque is measured by the product of force and the radius at which the force is acting. That is, torque is equal to force into the distance moved. Now, in the case of DC motor, we are discussing about which type of motion is. It is not linear motion, it is a rotatory motion, okay, or a circular motion. So, in the case of just imagine a particle moving in a circular motion, then in that case, what is the torque acting? That is, torque will be equal to force into the distance moved, right? Now, in the case of a circular motion, the distance is what? It is the circumference. So, you can write torque as expression for the torque as torque is equal to force into 2 into pi into r, right? And here you can write this as the radius r. So torque is given by force into 2 pi r, where r is the radius. What is this 2 pi r? This is the distance moved in the case of a circular motion, that is, which is actually the circumference. Got it? Okay. Now we will move on to we will try to derive a relation between power, torque and speed. This is also a very important relation. Okay, now we will see what is the work done per revolution. Work done per revolution. What is this work done per revolution? That means in one revolution, what is the work done? That is equal to force into distance moved, right? So this is F into 2 pi r joules, because what is the unit for measuring work? It is joules. So work done per revolution, or in just one time when the armature is rotating, the work done is given by F into 2 pi r. Then what if it is rotating more than one time? Right? So let us take that as small n, that is number of rotations or revolutions per second. Okay, that is per second. So n is RPS, that is rotations or revolutions per second. So now let us express the relation as work done per second. That means in 1 second, the armature may be rotating n number of times. Okay, so what you have to do is the previous expression, you just multiply it by n. Okay, so you will get the relation F into 2 pi r into n, because now you are going to find the expression for the work done per second. So that expression we can do some rearrangement. So this same expression you can write it as, just to see, F into, I am taking r to this side. So F into r into 2 pi n. What is F into r? Already we discussed what is F into r, force into distance, that is torque. So you can write this is equal to torque into 2 pi n. So what is on the left hand side? Left hand side we have written work done per second. What is work done per second? It is a power, right? So what do we get? That is power is equal to T into 2 pi n. This 2 pi n we can write it as omega. Okay, so finally the expression which we are getting, see here, power, that is the work done per second, that is power is equal to torque into angular speed, T into omega. Okay, so how did you get the power? Power, how did you derive that expression for power? That is the work done per second. Okay, so how did you get the work done per revolution? That is when armature is rotating just one time, the work done is given by force into distance, F into 2 pi r. So if you want to find how many times, maybe the armature is rotating n number of times, then what you have to do it, you have to multiply it by small n. Then you do some rearrangement and finally you will get the expression power is equal to torque into angular speed. Now what is this omega? Omega is equal to 2 pi, I wrote it here as 2 pi into small n. So when I am taking like, just to see here, Suppose I'm writing P is equal to torque into angular speed, and this omega I'm writing it as 2 pi n, which means n is in RPS, that is rotations per second. Now suppose if you want to convert it into minute, what you will do? You will divide it by 60. So you can write it as 2 pi n by 60. So small n is in RPS and capital N is in RPM. Okay. So finally we got the expression for the relation or expression for the power in terms of torque and angular speed. Okay. Now this term is nothing. When you are dividing 2 pi by 60, you will get this term. Okay. Next we will see the different types of torque which are available in the case of a DC motor. First we will discuss about armature torque or electromagnetic torque. We usually represent it like TE. In some books it is T, in some books it is TA. So this is a torque which is developed in the armature of a DC motor. Now how we will derive the expression for that? So from the previous expression we got this, like this PM is equal to, that is power is equal to electromagnetic torque into angular speed. This is equal to TE into 2 pi n. Okay. And where, what is TE? Electromagnetic torque. What is the unit? Newton meter. What is N? Speed in RPS. Okay. This is the one expression. Now we will write another expression which we have derived before. This one. That is, what is the mechanical power developed in the case of a motor? Back EMF into armature current. Therefore, the two relations we have. What is the first relation? Both on the left hand side, for the equation 1 and 2, left hand side is containing which term? Power. Right hand side, so we can equate it, right? So now equating the equations 1 and 2, we will get TE into 2 pi n is equal to EB into IA. Okay, from this we can find the expression for the electromagnetic torque or TE. What is TE? TE will be equal to EB into IA, EB into IA by 2 pi n. Okay, that depends. If you want to convert that speed in RPM, then you have to use n by 60 instead of small n. Okay, so this is the expression. Now again, if you see here, instead of EB, you can substitute this as expression, that is EB is equal to 5Zn by 60 into P by A. Okay, and finally what you get is this, that is all other terms you can take it as constant, as I told before. That is Z is a constant, 60 is a constant, this is a constant. Okay, and also this 2 pi is a constant. So all these constants we can take it as a single constant K or something. So finally the expression which you are getting is torque is proportional to flux into, this is another very important relation, phi into Ia. Using these torque equations, speed equations, we will be deriving or we will be analyzing the characteristics of motors. Okay, so when you draw the characteristics of the motors, we will be using these equations that we will see later. Okay, so torque expression we got as torque is proportional to flux into armature current. It depends, like when you are considering, for example, when we discuss about series motor, you will understand it better. But for the time being, just understand that in the case of a series motor, same like a series generator, in the series motor also, there is only one current. The line current is same as the armature current, and which is the same current which is flowing through the series field winding also. So here the flux, in the case of series DC motor, the flux is proportional to the current. Okay, so when you write the expression for the torque, torque is proportional to flux into Ia, right? But this flux is proportional to Ia in the case of DC series motor. So the expression will become like this, that is torque is proportional to square of the armature current. And this clearly explains why DC series motor is having a high starting torque. Because since the flux is depending on the current, the torque will be proportional to the current square. Now what about the shunt motor and separately excited motor? Shunt motor and separately excited motor, if you see the field winding, the voltage, input voltage V is applied directly across that field winding, right? So the flux remains constant in the case of shunt motor. So obviously what happens is torque will be proportional to current because phi is equal to a constant. So we can say that this shunt motor, DC shunt motor, is a constant speed motor. It is usually used for such applications, whereas DC series motor is a variable speed motor. So whenever you need a very high starting torque like hoist applications, you can go for a DC series motor. Okay. Now next step is how you can reverse the direction of the electromagnetic torque. Because the direction of the torque in the case of a DC motor It depends on the direction of the flux, okay, and the direction of the current in the armature conductors. Either you can reverse any one of them if you want to reverse the electromagnetic torque. But what will happen if you reverse both? Then there will not be any change in the direction of the electromagnetic torque. So this is about TE or TA, that is electromagnetic torque or armature torque in the case of a DC motor. So very important relation is torque is proportional to flux into product of flux and current. In the case of shunt motor, torque is proportional to current. So if you are drawing the characteristic, in the case of shunt motor, it will be linear relation. Whereas in the case of series motor, if you take, there will be difference. Okay, that we will see later. Okay. Next, we will talk about shaft torque. So whatever torque which the motor is generating in the armature, is it available at the shaft? Because the mechanical power we are taking from the shaft, is it available at the shaft? No. Always the torque which is available at the shaft will be less than the armature torque because we have to consider the losses. Okay. So now we are going to derive an expression for the shaft torque. The torque which is available at the motor shaft for doing useful work is known as the shaft torque. And how do you represent this? TSH. Okay, TSH. Now we will derive the expression for the shaft torque. Okay, already we have derived this expression, that is armature torque or electromagnetic torque. And just remember this relation, P, power is equal to torque into angular speed. Okay, and this omega we will write it as always 2 pi n by capital N, okay, 2 pi capital N by 60, where capital N is the revolutions in RPM. Okay, now first we will, so we understood that TSH, that is the shaft torque, will be less than the armature torque. How much it will be less than? It will be like TA or TE minus some losses will be there due to iron and frictional losses. Okay, so the iron and frictional losses, that is power loss, we can write it as P loss by, again by omega. Omega is 2 pi n by 60. So just I will write it as omega. Okay, so this is expression which we are using for finding the shaft torque. Now what is expression for this electromagnetic torque? EB into IA, that is a power. So this is the power term and this is the angular speed or omega term. So you got the expression for TA. Okay, now we will find the expression for this one. So this one already we got it. Now what about this one? Omega is 2 pi n by 60. What is P loss? That is iron and frictional losses, that you have to find. Okay, so this one, this is same as this numerator. So the numerator of this expression is this one and omega is 2 pi n by 60. And substituting these two expressions, we can derive the expression for the shaft torque. See here, TA minus TF. So the denominator will be omega 2 pi n by 60. Numerator will be the EMF, that is EMF into IA, that is a power which is generated in the armature minus iron and frictional losses. Okay, and finally you will get the expression for the shaft torque. Okay. Next we will discuss about the speed equation. Already we discussed about the voltage equation, then we discussed about the power equation, then we discussed about the torque equation. Now finally it is a speed equation. This already I think I have explained in the previous session. So let's first look at the back EMF, because back EMF is directly related to the speed. They are both directly proportional. How does the DC motor regulate the speed? By adjusting the back EMF. That is, when the speed has to be increased, back EMF increases. When the speed has to be reduced, back EMF gets reduced. Okay, so this is the first expression for the back EMF, that is phi Zn by 60 into P by A. But this is the second expression. Now let's equate these two, because left hand side you can see here both are back EMF. Now we will equate these two expressions and then we will find the equation for the speed. So finally we get it something like this, that is N is equal to, so as I told you, all the constants, this is a constant and this Z is a constant. Okay, so what is V minus IARA? V minus IARA is a back EMF. So this is expression. So we get it as speed is proportional to back EMF by flux. That is, when the back EMF increases, speed increases. When the back EMF decreases, speed reduces. So what about the flux relation between flux and speed? That is, speed is inversely proportional to the flux, which means If the flux is more, speed will be less. Okay, if the flux is more, speed will be very less, and if the flux is less, speed will be more. So it is inversely proportional. Okay. Now let's derive another relation, that is, usually this is for comparison, that is when sometimes you get problematic questions where like they will ask initially the speed is this, later on the speed is changed to a particular value, and how can you find this is some of the questions normally asked in the exams. So let's take the initial speed of a motor as N1, okay, current as IA1, and EB1 as the initial back EMF, and phi1 is the initial flux. So when the speed is changed accordingly, speed is changed to N2, the current will change, back EMF will change, and the flux also. So first expression is N is proportional to what? Back EMF by flux. Okay. So suppose if N1 is the initial speed and EB1 is the initial back EMF and phi1 is initial flux, then you can write N1 proportional to EB1 by phi1. Okay. What is EB1? EB1 is equal to V minus IA1 RA, where V will be a constant and RA, that is the armature resistance, will also be constant. Now let's imagine that the speed is changed. Now the speed is changed to N2. So N2, applying the same relation, that is speed is proportional to back EMF by flux, we get the second relation as N2 is proportional to EB2 by phi2. What is EB2? V minus IA2 R2. So here you can see the quantities or terms which are changing are what? Current, back EMF and flux, right? And speed also. Okay. V remains constant and RA also remains constant. Now you can take the ratio, that is the ratio of the change in the speed. So the new speed N2 divided by old speed, that is N1, is equal to this relation. Here you have to consider this term. In the case of shunt motor, the flux is constant, right? So you have to consider only the ratio of the back EMF. But whereas in the case of series motor, it is not the same. In the case of series motor, the flux is not constant. The flux is proportional to the current. See here. So when you write the expression, it will be like N2 by N1 is equal to EB2 by EB1 into, instead of phi1 by phi2, you can have to write IA1 by IA2. So when doing these problems, you have to be very careful just to see which type of motor they ask the question. So if it is shunt motor, phi1 by phi2 will be a constant. You don't have to consider that. Okay. Whereas when you are doing a problem related to a DC motor, you have to keep in mind that the flux is not constant. It is depending on the current. So when you are trying to find the new speed of the motor, you have to consider the flux also, the change in flux also, if it is proportional to the change in the current. Okay. So this is about the torque. So today's session we discussed about the concept of torque. Okay, what is torque? That is force into distance. Right. Let's have a review of that. That is force into distance. Then we discussed about the relation between power, torque and speed, angular speed, that is P is equal to T into omega. Then we have discussed about the torque which is available at the armature, that is armature torque, the expression for the armature torque, and we found that is proportional to product of flux and current. In the case of shunt motor, torque is proportional to current because flux is constant. In the series motor, torque is proportional to square of the current because current is proportional to the flux is proportional to the current. Then we discussed about the shaft torque, the torque which is available at the motor shaft, and this will be less than the armature torque. And why it is less? Because we have to consider the iron and the frictional losses, and we derived the expression for the shaft torque also. Okay, so then finally speed equation, that is speed is proportional to back EMF by flux. Then we discussed about the relation, that is what is the difference when you consider the shunt motor and the series motor. That is when there is a change in the speed, what are the terms which we have to consider. That is in the case of shunt motor, flux is constant. That is speed will be, the ratio of the speed will be proportional to the ratio of the back EMF because flux is constant. Whereas in the case of a series motor, the ratio of the speed will be proportional to product of the ratio of the back EMF and the ratio of the current. Hope this is clear. Okay.